It's almost like everything I ask in this whole class is predicated on the other things that we've done in the class. What? Built on. Create the structure for. Okay, how's everyone doing? How's your weekend? Long? That means you were studying the whole time, right?
No. And no signal.
No what?
No signal. No service.
Oh, okay. In the desert. Okay. So you're not ready for this?
No.
Okay. All right, well, you have 40 minutes. No, just kidding. You really don't. Okay. No, today we are going to finish up the discussion of just really quickly towards the end of chapter 6, 7. He discussed something that we call the Down inversion, and it was all about how we wanted to put the potential, the vector potential, and the scalar potential. We wanted to combine these concepts because we're realizing that there's this like deeper connection between the two. So we're going to draw those links, and then we're going to get into chapter 8, which has to do with conservation laws, which has to do with the idea of work and power. And this is going to lead us in to the discussion of light. And they call it radiation. And we'll see, of course, radiation is light. We know that already, though.
Yeah.
Okay. Do people have homework to do that they want to?
No.
Okay, I'm just saying, if you have an old one, I'm gonna start, wants to see that old homework come back in, so they can see the grade continuing to go up.
I've done half of each one, so that any.
Okay, all right, that's fine. You also don't have to have them stapled, you can like pull them apart in the back. If you're gonna be doing the check-in, I will expect you to bring all of your completed work. Right, even if you got a stamp, I gave it back to you, and you worked on it more, that's good. I want to see that improvement, right? If you're doing the test, of course, it's just a normal test. I'll just sit here at the front. There will be a book. You're permitted to bring your book, no notes, and a pencil or pen. I'm going to prefer pencil a lot. No iPads written. Yeah.
Digital book.
If you don't have a digital book, let me know. Or if you don't have a physical book, let me know, and I will get copies. You won't need a calculator. Come on, what do you think this is? Some math class?
I don't know.
What's that? I mean, maybe you'll need a calculator for like 4 times 24. Like for me, sometimes those can be the hardest ones, and you're supposed to know them. Right. But you can also just leave them in 2 times 3 times 4 times 6, and that's okay with me. Because this again is not a math class, it's a physics class. Physics is not math.
I have a 4.6, so I have one of the questions from one of the homework we done. I'll be passing to you right now.
Yeah, we'll do that at the end.
We're gonna have to check in, just like.
Yeah.
Oh,
Okay. Any other questions about the test?
Great question.
I never said how many questions.
Yeah, but it's like 20.
So for the check-ins and the test, you'll see very similar problems. They're homework style problems, right? They're just
More or less than 10
more or less than 10 what?
problems.
Oh, no. Less than 3, I would assume. Probably 1. And probably maybe 2, probably 1. And I'm identifying whatever people had the most trouble with. That's what's gonna be on your test. That's what's gonna be in your check-in. So whatever you didn't understand the most in your own work, look over that. Right? All of it. Starting at the beginning. Okay. Does that make sense? Okay. Other questions? Okay, so we did this a couple times. I'm just gonna try and summarize it again here. We talked about the Maxwell laws, and then we wrote them in the context of the vector and scalar potentials. And we showed that you could write this. We showed that you could write the electric field as the divergence of the potential. But there's a contribution to that. And there's a contribution from the vector potential. Now, what is that contribution? So what?
Minus the TA next week.
Exactly. So minus the time derivative of the vector potential. Right? So this essentially says that my electric field is due to my scalar field. And we know that the scalar field is related to where our charges are, distribution of charges. And our vector potential is due to change of B field, right? I could also think of this in terms of like currents. So this currents give rise to this, and charges give rise to this. So I look at the contribution from both, and I get where the E field is, right? Okay. And then I got to write something really fun. I wrote that the charge density, or sorry, the minus charge density was del squared V plus ddt of the divergence of A. Right? And that was the same thing. I just took the gradient of this. So now I have something that tells me how to find where the charge is from both potentials. I'm just combining the potentials. Okay. You got that fun equation, right? Where you can have something like this. What's this thing?
I know what it is.
This French, good. What? The bon time. That's close. Some of those letters are right. Okay, all right. We're getting a lot more letters. It's D'Alembert. You will never be tested on whether or not you can pronounce it, but it is fun to say, right? So this one here is what? The Laplacian. So now you've got that one. So this one is just the next one. See, triangle squared. Triangle squared. It's right. Okay. This one here, and I'm just making this up. This has nothing to do with it. See the three sides?
Yeah.
3-dimensional gradient.
4-dimensional.
4-dimensional gradient, right? Because what does this equal? Very good, but not quite.
Yeah, it's Laplacian minus epsilon naught increase.
Right.
So it's
Right. So 3 spatial dimensions and 1 time dimension. And the quantity squared gives you the square root there. So we said that this minus all of this jibbity jab is just this. So now I have something that relates the potentials to, right? So this is the scalar and vector potential in terms of the charge, and this is the scalar, the scalar and vector potentials in terms of currents. Right? So now we should, generally speaking, be able to describe these situations. And what I'm going to do now is essentially mathematical mumbo jumbo. Okay, we are going to introduce something called the gauge. Are you familiar with the gauge? Okay, so you may have heard of something called gauge freedom, and that means that you're allowed to make specific choices because these things, these abstractions, we take gradients of them to get the physical object, or we take curls of them to get the physical object. So what that means is sometimes we can tack on terms, just like you know how when you're integrating, and you add some constant of integration because you know that that'll disappear later, if you were to take the derivative again. We're gonna use that same freedom here in these derivatives and the curls and the gradients, because we know that certain parts of those will disappear. So even if I add something to A, excuse me, or if I add something to V, I'm gonna add it in a format so that it disappears when I get my E or my V out. That makes sense? So it'd be like you have some formula and you know you're gonna take a derivative with respect to X, so you just add a number to it. Right? Just a number like 45 or 6 or minus 30, whatever. And that offsets the entire formula up or down. So this is what we mean by gauge freedom. We have the ability to shift the entire, it's not a formula, you know, it's a real thing, but we have the ability to move it up and down because we know that it'll be deleted later. Okay, so conceptually that's what I'm about to do, but it's gonna look weird. I promise it's mostly fine. So we can impose conditions in A and V as long as they don't change E and V. So let me just write that. Oh, sorry, not plus, but you know, and. Same concept. That's the definition of gauge freedom. So how does this work in practice? What was the rule? How do we get B from A? What's the relationship there? Del dot A. All right, raise your hand for this one. Well, it's only one of two, so we gotta flip a coin here, folks. Why is it curl? What? Because that looks weird. That doesn't look right to me, so I don't like it. So in fact, this is why we call this the vector potential, remember? Let's look at the missing vector symbols here. So if I do this and this, then this dotted into this would not make this a vector. Okay. Okay, so this needs to be a cross so that they can be vectors. Correct? Okay. So why do I care about that? So we know a fun property about curls of divergences. So because I have this thing, I can modify it. So I can always take A and I can add what to it and still get back the same B. What's that? Divergence of something. Okay. So I can always take this, right? And A can become A plus the divergence of lambda. Or lambda is just another thing, right? Because as long as it's the divergence of this, then when I do this cross product, it'll disappear. And that's okay. That's legally acceptable. Let's see if I write that down. This is gonna look like, oh god, I'm running out of space again. Why did I always do this to myself? All right, here we go. It's even like I meant to. There. Okay. So here's B prime, and that's gonna be del cross A, but A is now A plus del dot lambda. Okay. And so then this can be added to both terms, del cross A plus del cross del dot lambda. And this is identically different. So A, B is just B. Great. Make sense? Is that motivated or no one cares? Okay, that's fine. What about for V? Curl to it. Clever. Clever. You could add a curl to it because then what would happen? Right, you just reuse that same one. Let's see how that works in practice. Okay, so let's say we take V, and we're gonna say that that is, you know, V prime is equal to V plus beta. Okay. For this first one up here, we have E is equal to minus del V plus ddt of A. Okay. So we should be able to use this piece and this piece to figure out their relationship to one another. And that'll tell us a little bit more about these random symbols that I just threw up on the board. Right? Because there's a relationship between that. We want to understand what these fields really are doing with respect to one another. Okay. So this piece here, del dot V, will be del dot V plus B. This is really beta, not B. All right, should be more specific. Okay. Plus ddt of A plus del lambda. Okay. Okay, this equals E, right? So this term and this term need to equal E. So this term and this term need to equal 0. Why is it 0 and not scalars? What? Yeah, can't affect it. Right? So based on our rules of gauge transformation, we need to be able to add whatever this is and whatever this is, such that when you go back to get E, nothing changes.
If it was a scalar, would it the derivatives be 0?
That might still be the case, right? That might be a unique solution that does work. But we do know that there may be configurations where maybe something changes in time and something changes in space in such a way that those two contributions cancel out and they don't show up in the E field. Does that make sense? You're right that taking derivatives of a scalar, taking derivatives of a constant, those might cancel out too. But our goal here is just to set them such that these contributions that they add to the E field is 0. Okay. All right, so let's set that equal to each other. So I have 0 equals del B plus, that's not B, sorry, I should stop saying beta ddt of del lambda. Okay, the del's come out. And so I can say, oh, that's not how that happens. Del's come out. So beta plus ddt lambda. 0. Now what would you do?
Find the gradient formula.
You would apply the gradient formula here? That would be the right thing if this was something. If this was anything other than 0, I would say yes. And I'd have to open my book and I'd have to look at it. But remember, we're using the fact that del's and crosses are all disappearing here. So if this whole thing equals 0, then what does this thing equal? Nope. Not necessarily. It could be, but not necessarily.
Negative.
We don't know what beta is. Beta is just a thing.
Gonna be negative 1/3.
Okay. You could do that. You don't have to. Yeah, it won't matter. You'll see. You'll see that when we write it this way, and maybe we need to write it like this up here. You know, maybe that's the easiest way to do this. But you'll see that beta is just an offset, it's a constant.
Are you saying we should have them equal to each other? That's negative. One should equal to negative the other.
One should be equal to the negative of the other.
Yeah.
So that would be 0 on the inside, but it's del times this, that's 0. Let's imagine this is a one-dimensional problem. Okay, if I write it like this. Now what is it? What was that?
So just a constant.
The whole thing is a constant. You see?
I've been constants before even that.
Well, certainly this thing is probably a constant. This thing is not a constant because it has a time derivative in it, right? This thing is by definition not a constant. But this whole thing together is a constant. Right? Okay. Let's rewrite this properly now. Okay. So then let's look inside here. Okay, so this whole thing equals a constant. Beta plus d t lambda equals some constant. So now I'm going to do the annoying thing. Not that this wasn't already annoying. This constant and this is a constant, so let's add them together to form a new constant. Okay, so now I'm going to do ddt. Okay, lambda equals beta. Fun, right? I told you it was mathematical mumbo jumbo, but it will get us somewhere. Okay, can we solve this?
Beta times t.
Yeah.
This is not just a constant.
Yeah.
Okay, but we don't know the formula. We can't just solve it unless we know what lambda is. But we do now know. Even so, it doesn't like think about lambda can be anything, right? E to the t could be a sine wave. We don't know what it is, but now we do know that it is related to b just by this. Okay, so when we add a gauge transformation, v minus b, okay, I'm really just adding this thing. So this is b over here, right? So if I'm modifying the equations for v and the equations for a by beta and lambda, I'm not actually changing them by two separate things. I'm only changing them by one thing, and that in this case is lambda. See? Yeah, let me show you because it'll be easier when you see it on the board. So we have a prime and we have v prime. So this is equal to the old ones, a, and the old one, v. Okay, this one up here, we said, okay, I'm just going to add del lambda. And this one here, I said I was going to add beta, but now I know what beta is. Beta is something with lambda. So beta never existed. It was always lambda the whole time, right? That meaningful? Okay. Okay. Okay, so why do we care? We care about this because we can adjust the divergence for the A to simplify things. Okay. What do I mean by that? Let me write this down then. We can. So let's say we have magnetostatics. We can use something called the Coulomb gauge. Del dot A equals 0. Okay, this is called Coulomb gauge. I'm missing a U right there. Okay. And if that's the case, what do you have here? This one? Yeah, 0. Perfect. So in the Coulomb gauge, in the magnetostatic stage, this whole term disappears and you get back the thing that you know and love. That's really simple. That's del squared V equals rho epsilon, right? Oh, minus, sorry. I always forget things like that, so if you keep me honest, that'd be great. Okay, so we can use this gauge in the dynamics. V doesn't alone give you E. You need E and B together. So generally speaking, you will use both. The advantage of the Coulomb gauge is that V is easy. The disadvantage is that A is really hard. Generally speaking, A's can be annoying, but we can try a different one. Can I get rid of this part? I won't make that anymore, right? What about the Lorentz gauge? So we can say something like, instead of picking del dot A equals 0, let's make a choice. We're gonna make a really smart choice because Lorentz was a smart guy. He's gonna say del dot A is gonna be equal to minus mu naught epsilon naught dv dt. A reason why that might be helpful.
Yes, over there.
Exactly right. Okay, so you make this weird choice, and then this thing over here becomes just the del inversion for J. So we have del squared A minus mu naught epsilon naught dT squared. Remember, that's the del inversion, right? Equals minus mu naught J. And interestingly enough, We look over there. This piece here, this is not so obvious, right? This one's obvious because this minus that, right? This is the opposite of that. So this term became 0. You can't quite see it here, but it's also up here. You're gonna add another ddt, and you're gonna have the del squared. Okay. And it's gonna look like del squared v minus mu naught epsilon naught ddt squared v equals minus rho. Okay. So this is really beautiful when you simplify it with a del inversion sign. But it just looks like del squared or box squared a equals minus j, not j, and box squared equals minus rho over epsilon. You might be saying yourself, what the fuck? Who cares, right? Okay, there's something incredibly beautiful in how simple this is, and incredibly powerful. Okay, who's familiar with special relativity? Maybe heard the words in those order. Okay, and the basic premise here, people tell this story. Einstein's on a train and he's headed to work. Super bored on the train every single day. No podcasts have been invented yet. There's no baseball on his TV. There's no internet. There's no TikToks. So he's just sitting there and he's looking at the clocks. Because every time that he's on the train, there's a clock tower and it tells you what time the train is going. Okay, he's on the train, he's on the train. And he's realizing each one of those clocks run their own times, but they're not always the same as the clock on his watch, right? Because if you think about this in an abstract concept, as you head towards the clock tower, you would be moving fast. And let's say the light has a finite speed, then you'd be moving like closer, right? So you'd get that information. Clock would have a different time. And he goes through all this thing and he's realizing, well, wait a second. As I'm headed towards there, if the speed of light, can be whatever it wants to be, then, you're going to run into some really unusual issues, right? So he essentially is looking at these clock towers and he's saying that the way that we experience things, whether it's from the perspective of the person sitting in the clock tower watching the trains go by, he's not moving. Time seems standard for him and it's going along, versus someone who's moving quite quickly towards him, versus another train going by in the opposite direction. They're all experiencing what they would perceive, let's say they're moving at a constant velocity, what they would perceive is being at rest and other things moving towards them or away from them. And yet they might look at one another's clocks and see different times, not because they were started incorrectly, but because of how long it takes, right? Like imagine for any clock, you have a clock that's going like this, pendulum type of clock, that relies on, I don't want to get too far into this. Well, basically clocks run different amounts, because of general relativity. Have you heard about this? So this is how we use GPS. If you're lower, closer to the Earth, the clock runs at a different speed than if you're higher up. But he found that essentially for the purposes of what he was talking about, that events are not simultaneous. And that in particular in special relativity, that there is not a preferred location in which to view physics. So if I have 3 different, what we call inertial reference frames, someone's sitting in a tower, not moving. Train going this way, in their perspective, if they're not accelerating, they don't feel like they're moving. This train going the other direction doesn't feel like it's moving. Those 3 all have to agree. Okay. However, currents are what? Charge or charge moving. And this is charge. So here's charge and here's charge moving. And suddenly we have a deep appreciation for the fact that if I am in a reference frame that's moving, say in the same direction as a current, that will not look like it's moving. Now it'll just look like charge. And yet, the B fields and the E fields that come out of it need to always agree, regardless of whether or not you're moving in any of those directions. And they can be shown very easily in the Lorentz gauge, because here, let's say I am moving in the same direction as the current, suddenly that just becomes the charge, right? And anything that was, just charged, now that I'm moving, becomes current, right? And these currents give rise to both A and B, and both A and B, right? Maybe I should have introduced that when we talked about special relativity only. I don't know. It's just like fun. It's like everything you've all learned boiled down to that. It is cool, yeah. And then it gets a lot harder. It's like back out again. Okay. These are wave equations. We'll see that more when we think about this is towards the end of chapter 10, if we make it that far. Fair enough, we'll make it that far. Questions about this format? Okay. Let's talk conservation laws. How much of chapter 8 did y'all do? Did you even do chapter 8?
Who was
Are you just saying that? So that
If we did, I don't know.
okay, I don't know if that's okay.
What
Well, yeah, what is it?
Conservation laws.
Oh,
Or at least the first part of it is. I think there's also some stuff about there like work and other.
Maybe.
yeah, I'm double for
Okay,
Yeah,
so
I remember.
you do remember work. Yeah, I mean, you've probably seen work from, the first time you do work in a E field is like the 2500 series. So it like exists in the back of your mind. Okay. But what are conservation laws? What does that even mean, these words in that order?
Changing certain things to be zero.
Okay, yeah, so that's the idea that like certain quantities don't change. Before E and M, give me some examples of like conservation laws that you have come across. Conservation of mass. Okay, we don't create mass. And that's true when.
Except for E equals some system.
Okay, yeah. So that's true in most cases, but in fact, I do create mass very often. Right? So in like the universe as a whole, there are stars. There's stars that are converting mass into energy and energy into mass.
conservation of energy.
Conservation of energy, what does that mean?
These energies.
Okay, what is that true? What does that mean?
An isolated system.
Okay, so maybe in an isolated system, we might convert from one energy to another, but we can't just create it. Now, or destroy it. When would that not be true? Like say in a more like normal application, not just in a closed system. Let's say you have a closed system, but energy is not conserved. Example,
Because you use the energy
Sure.
and move something.
Yeah, like going to the gas.
Car, yeah, so like a system where you like do work, right? Take that energy, convert it to work, but you can still add up that work, right?
Yeah.
Okay, anything else?
Yeah, my phone's dying.
My foot dying, it doesn't do conserving its energy well. Not quite what I mean by that, but what about friction? Is that a conservative force?
Yes.
When we think about conservative, or we think about conservative energy, we usually tend to think of it in terms of being able to go back and forth between different forms. Can I ever take the form of friction and put it back into potential energy for the purposes of like getting my tires rolling again?
No, but to make it not conservative.
Yes. I know, that feels uncomfortable, but generally speaking, that's what we mean by conservative. Okay, so we talk about the word conservative as being able to go back and forth between states without loss. That is the definition of conservative. Okay? So let's look. I'm going to tell you the first global conservation law. You maybe already know this. Okay. Or maybe, do you want to guess it or you want me to just tell you? Just tell it. You don't like this suspense, right? You're like on the edge of your seat. Okay. The first one, the first global law is that all charge is constant. In the universe. You have to sum over the whole universe. Reasonable? Would you have guessed that? It's just not true. The universe is not net positive or net negative, and it's not growing in either direction. Well, it could be net positive or net negative, but it's not growing in a certain direction. Would you have guessed that? Totally. Yeah. Yeah, I mean, if you think about it, it's a little out of pocket, right? It's like looking around at everything that we know about our lives. We say, well, generally speaking, like on Earth, things that are net positive, you know, they attract stuff to them and then they become uncharged, right? And so then you say, well, like if I drew a box around the Earth, you probably have a good balance there between pluses and minuses, right? And to make a statement like this is pretty wild. The longer you think about it, the dumber it sounds. Because essentially that's saying total charge is constant. There's no way to produce or remove charge. There isn't, but you don't know that. Okay. All right, now locally. If local charge changes, then there's a flux. Through the surface. It did not vanish. It moved. Okay. And this one kind of makes sense. Kind of makes sense. What is this similar to? Yep, it's definitely conservation of mass, right? Feely, right? Says that like I can't create new mass carriers. I have something that does my mass. And then I just have to keep track. If the charge went down, they went somewhere else. So we can relate that with this. Where time's that? What's that part say? Okay, have you ever sinned before in your whole life?
Yeah.
What class that you took with me last semester?
I'm gonna say,
Fluids, that looks fluidy to me. No, not fluids again. I deleted all of that. Okay, what about if I wrote it like this? Stop! That's a crime. Okay, so this looks really similar, right? So before, what was it?
Before in static was 0.
No, sorry, in fluids,
Oh,
in fluid dynamics. Do not recall.
Or like the formulas we use or?
That's it.
oh, we're.
Right, in fluids it look like that. What does that mean?
Oh, what comes into.
Okay, so if I'm eating stuff.
Mhm.
Okay, then I'm gonna have to change my stomach size.
Was that a velocity?
This is velocity, yeah. Remember the divergence of V was like how you're moving in and out? Does the box change? Say that again? Looks like a U. I'm sorry. Better? Okay, so in fluids it was like that. And in E and M it'll be like. No, Chris Bonnie, not again. Shit. What does I mean? What is the word for it? Current, exactly right. Looks so similar. No or yes? Okay. So in English, what are we saying? We're saying that if there is a change in the current, sorry, if there's a change in the charge here, it's due to that charge moving through the surface of whatever box I'm considering the total charge in. So let's say this room exists and all the boys in here are positive charges and all the girls are negative charges, and then the ladies leave. Now there is a net negative charge differential, and therefore you're left with positive charge, or vice versa. All the guys leave, and all the positive charge is going out here, and look at the negative sign, right? It's leaving, therefore leaving you with less negative charge. Does that make sense?
Stay with that first thing one before you do the example.
This piece?
Yeah, no, you explained it.
Oh yeah, so this piece here is what? What's that? Yeah, so this piece here is the thing that we would measure, say in this room. And say I take a snapshot right now, and I see how many people are in the classroom. And then in like 40 minutes, I take another picture and I see how many people are in the room. Okay, so this would be the change in the total number of charge in the room per unit time. Right, that's how we define this differential. The change in charge per unit time. And this is due to the flux. How is it going in and out? Right? In particular, the flux of current with time. Okay. Want a picture of that, or we got it?
Yes.
Want a picture?
Yeah.
All right, we have a box. And we have some charges. Okay. This is at time 1. At time 2. Oh shit. Okay, at time 2, same box, same size. We're not going to change the size of the box, but that is something we could do in fluids. We're not going to do it here. Okay. The same charge state? No. What happened? Lost positives. Yeah. How many positives did I miss?
Did you just count for us?
No, I counted the negatives.
I can't tell in the top light.
Lost 7. Okay, so I lost 7. So how did that happen? So there's a picture here. Now in between this picture. Okay. The box. The 7 charges split out. Does that make sense? Another way of viewing that. This is me at the beginning of the morning. Okay. We're gonna review this in backwards form now. Okay. Hungry. Not enough positive. Okay. Adds breakfast burrito. Right. Run that backwards. Right. Mostly happy. Okay. So this is that version that we talked about here. How do we get larger? Eat some food. Right? You have a bad night, Friday night, ooh, okay, and then you get a little bit smaller. Yeah. Okay, the one that's actually helpful. This one here. Okay, so you start with some distribution of charge. Okay. And you notice at the end that there is a different distribution of charge. Our statement about conservation of local charge says that in order to get rid of charge, it has to flow through the surface. So it has to get out of the box. I can't just take the positives and negatives and run them into each other and make them disappear. I have to physically remove them or add them from the location. So at time 1.5, I removed 7 of the pluses in order to get the final state. Okay. Okay. What about conservation of energy and momentum? Like those or no? 2. Good. We like them. Okay, good. All right. So let's write this as ddt of u. Okay. So this is going to be the total energy from both E and B, and mechanical energy, if there's any. Sure. So this is going to be equal to surface integral of S dot dA. It might be a constant out right here, but I'm going to ignore that for a second. We're not going to define what S is yet. We'll get to that in a few seconds. Okay. We're going to say that U total is U E and M plus U mechanical. And I'm going to define this a little bit later, but we're going to call it the energy flux. I know that's really bad. That's good. Okay. So does that make any sense, what I've just written? Yes, it does make sense. Because this formalism is the same as this formalism. In fluid dynamics, we showed that if you write it this way, then you can use Stokes' theorem to also write it this way. That there's a relationship between contours over a closed surface, right? And the divergence of that surface. So I'm saying the same thing 2 times. Right? Because here, if you write this, and you look at the total charge, you say, well, oh shit, this is a closed surface because that's the box. And it crossed through the box in order to get out. right? Whereas here, I'm saying the same thing. I have some amount of total energy that's due only to the flux of S through the surface. Have some box. If S goes up, right, then U gets bigger. If I have the same amount of S going in as going out,
So whatever's in there is constant.
exactly. So U is constant. Okay. So this is intuitive, and we get that one now that we understand this one. So let's look at what it actually looks like. So folks remember how to write the electromagnetic energy section, these here. Yeah, work for energy, if you want to call them.
The electric field, for the work of the electric field, wasn't it like the integration of E squared?
Aha, okay. That's exactly right. And generally speaking, you're doing this over all volume. So I'm gonna add both of these together. It's gonna be E squared over mu naught. Okay. What this generally says, so here's the first term. Here's the second term. So I just get my energy from the electric field and the energy from the magnetic field. I'm gonna sum them up over the whole space. And that's the energy.
No magnetic field not important.
We'll see. Hold your horses. Okay. So the work is done here to store the energy in the fields, that is to say the total E is in the fields, okay. So we would love to know what the energy flux is. Eventually we're gonna get to waves and we'll show that we can transfer energy from one place to another. So we're gonna sort of come back to this idea of how E and B can be related to one another. Right, B can still have energy, right? The question about whether or not it can do work is slightly different. Okay. So what is the concept of work exactly? Just like conceptually speaking, if you were to explain it to, you know, a 10-year-old.
Isn't it just like the amount of force over the distance between, or?
Exactly, right? So force times distance is the rough idea. What? Not something you'd say to a 10-year-old? I don't know when you start saying that to kids. I don't know if you ever start saying that to kids, maybe you don't. Okay, so you say something along the lines of, you know, work is dW, is equal to F dot dl. Oh, great. And then what would you have to do? Let's say for a single charge. Just generally speaking, most general.
Wait, do you want to know the magnetic field? Or do you want-
Yeah, just we're talking about electric forces on, say, a charge. Electric magnetic forces, generally speaking, most general that we could ever do.
Isn't the force, let's say for a point charge, the force would be Q times the electric field.
Okay, that's one of them.
If we wanted the magnetic, then it'd be.
have here,
What you got?
L, then F top. But, oh, plus Q, the weird V cross V.
That's a weird thing.
Oh, yeah.
Oh, you just don't like my V's, huh? Okay, what about just view cross V, okay? What if we do something like V cross V, is that okay?
Yeah, no,
Have we seen that before?
So
Yeah.
it's,
yeah, that's the,
Why is this a weird V?
they wrote it as dominant.
Alright, that's fine, I'm not gonna cry about it. Alright, so this piece here is a distance. And generally speaking, we might have the V, because we're using it right here, so I'm gonna include it, I'm gonna rewrite DL. As V, like this one. V dt. Is that okay?
Yeah.
Okay. All right, so then I can say something along the lines of dw. And I can put the dt on the bottom here, so I'm gonna do dw dt is equal to qe plus qv cross b. Okay, all times v. Right. What is this one equal? Try to write it in whatever symbols look the best. Rolando already said this today.
Like, that makes it-
What?
like, having something. That has to do with something, too.
Yeah, it definitely has to do with things like builder to be there, right?
10%, 50%. The equation.
So let's look at what it means. It's not about, it's not memorizing what they are and then being able to reference it. Let's look at what it means, right? This first one means QE. Which direction is the QE force in?
E,
In E. That's the obvious one, right?
Yeah.
What about the V cross B force?
perpendicular to the velocity and
Perpendicular to the velocity. And what does the work mean? Force over distance. Does it matter that they're directional at all?
oh, perpendicular to the work.
So here I have force and the distance. If I, for example, I got my door and I'm rotating it like this, left and right, right? Maybe I'm pushing on it that way. Or let's let's take that door and I'll push it like, here's the door, right? And then it rotates like that. I'm gonna push it from the side. Am I gonna get work done? No. Perpendicular. Okay. So 0. So here's the question. The force, the magnetic force, is in which direction compared to the velocity? We said so, right? Because V cross B.
Yeah.
You require it. And then I wrote DL in terms of, and now I want to take a del cross V and I want to dot it with a V. Look at it again. It has to be there. So Rolando said magnetic forces do no work. And he said it very loud and proud.
Oh,
And now we see it. It's super obvious. Because del cross B is not in the direction of V. It can't be. Right? But now I want to dot it into V again. You know what I'm saying? Okay. So we constructed something here, which does no work. Okay. So this is great, because then I just have dw dt is equal to E dotted into QV. Okay. If you wanna sum that up over everyone, let's say you have one charge, or you have like 6 charges or 40 charges, you wanna know what the total work is, and you gotta do the integral over the volume. So if I want. Then I have to do. Right. Because Q, unit volume, is density. You remember that one? The definition of this thing here is Q per unit volume. Charge. These are all the abstractions that I'm using. And then when I multiply my rho by my V, I have constructed. Too many. Charge that's moving is. Thank you. It's just E times J. Bada bing, bada boom. No charge move. No work. Pretty cool, right? Simple. Not complicated. Easiest class you're taking this semester. Okay, that's my half view here. Okay, so let's see if we can get through this first. Yeah, we can do this. No, you don't think so? Let's leave it for here for 1 second because it looks really complicated and simple, or really simple, not complicated, and I'm going to complicate it again. So maybe I don't want to lose you before that happens, because I think everyone needs coffee at this point. Do we have questions about the class as a whole? You see where we're going right now? Okay. The things that we're going to go over, not next Thursday. So for next Thursday, if you don't have a check-in, okay, you'll be taking the test. If you don't tell me before class, then I won't have a test for you. So what I'm doing is I'm looking at how many people are in the class. And then if you reach out to me about a check-in, I'll just remove your name. And then you'll do that with me whenever we make that time. Okay.
If Thursday no class, anyone taking the check-in?
Correct.
Okay.
Any questions? Yeah.
That's this Thursday.
Yes, so this Thursday would be a test in class. Questions about that process? Okay, well then I'll let you go 5 minutes early. For a question, yeah.
How do you go from here to that?
Here?
Yeah. You change or is it like?
Well, they're related, yeah. I'm just telling you that it looks like this. Okay? And we're gonna get to the part that's more complicated because we still haven't described what this is. So I said that S is some vector that describes energy flux. And it has a fun name. It's called the pointing vector. But you don't know what it is or where it comes from. And what we'll see is the way that E and D fields are related, the way that they distribute energy, and the way that they do work. If they do. All of this will kind of fall out of the next. When we go from that to the next one to the next one. Okay. You have homeworks for me? Did I give it back to you? Is that what you're asking? I don't know that they're all graded. But if you want yours in particular, you can come in and I give you. Can I give you that? Okay, all right. No worries.